Assalamualaikum and very good day to all of you. I am Nik Rashida from International Islamic University of Malaysia, and today I would like to present parts of my research progress entitled Dynamic Adsorption of lead by Novel Graphene Oxide-Polyethersulfone Nanocomposite Membrane in Fixed Bed Column. The growing world population, climate change, and water contamination are the global issues that faced by us nowadays. This problem will lead to the high demand of clean water worldwide. United Nations also expects that the world's population, around 1,800 million people, will encounter water scarcity by 2025. Lead is one of the hazardous heavy metals and major chemicals of public health concern. Lead contamination is associated to wastewater effluents from the electronic and semiconductor industry. This is very harmful to the environment and human health. Moreover, 17 Sustainable Development Goals by United Nations are the world's best plan to build a better world by 2030. The SDGs are a call for action by all countries to promote prosperity while protecting the environment. Moreover, this research is in line with SDG number 6 under clean water and sanitation, where by 2030 the world is expected to improve water quality by reducing pollution, eliminating dumping, and minimizing release of hazardous chemicals and materials. Therefore, strongly motivated with the SDG goal number 6 and previous finding, graphene oxide polyethersulfone nanocomposite, or known as GPN membrane, is fabricated to remove heavy metals, specifically lead, from the contaminated wastewater effluent. This GPN membrane is the integration of both nanotechnology and membrane technology. Recent developments in nanotechnology and membrane technology have further increased the effectiveness of adsorbent materials, providing innovative systems for improving wastewater treatment. Nanoparticle of graphene oxide is incorporated with a polymer solution to produce a polymer nanocomposite membrane, which have a dual function of adsorption and filtration. This novel GPM membrane consists of functional groups to the surface and pore wall of polymer membranes, where the target pollutants are selectively absorbed to the functional group. GPN owns its unique characteristics such as low energy consumption, high porosity, ease of fabrication, and strong mechanical stability. Due to the limitation of the static adsorption system, where the treatment of small volume of polluted wastewater and inaccessible authentic data for scale-up, therefore, dynamic adsorption analysis is the best approach to understand the irregular flow patterns and to obtain design models that could be applicable for the commercialization. Next, we move to the methodology. This is the schematic diagram on fabrication of GPN membrane. GPN membrane was fabricated by non-solvent induced phase separation method. The doped polymer solution will pour onto the glass plate to cast the membrane using casting blade. And then after 60 seconds, it was immersed into the coagulation bath containing the ionized water and left for 24 hours for complete precipitation. At the coagulation bath, the exchange of solvent and non-solvent takes place. The solvent migrates from the polymer solution to the coagulation bath, while the non-solvent follows the reverse path, leading to the formation of the membrane. The schematic diagram shows dynamic adsorption experimental setup. The flow rate of the feed solution was controlled by a peristaltic pump, and the solutions were pumped in a downflow mode. Here, the effects of initial feed concentration, flow rate, and bed height were investigated. Then, the treated sample at the exit of the column were collected at predefined time intervals, and the final concentration of lead was measured. Here are the results and discussion. This graph shows the result on effect of initial feed concentration, The breakthrough in columns with high feed concentrations was reached much earlier compared to the low feed concentration. Thus, a better adsorption performance is towards the diluted solution with a comparatively lower feed concentration. From this graph, you can see that the slopes of the curves became steeper when the flow rate increased from 10 to 20 ml per minute. This phenomenon can be explained by the reduced residence time of lead solutions in the column with increased flow rate, leading to an earlier breakthrough time. The last parameter is effect on the bed height. Here, 3 layers of GPN membrane were positioned in the column. An increase in the bed height shifted the breakthrough curve to the right and prolonged the breakthrough and saturation time. This result could be explained by the more available active site for absorption at the higher bed height because of increase in the membrane mass and also membrane area. For modeling the breakthrough, 3 models, namely the Thomas model, the Pohat-Adams model, and the Yun-Nelson model, have been used. From the nonlinear fittings, a good fit of the experimental data to breakthrough model is Pohat-Adams model, where a high coefficient of determination, which is R squared, and low sum of square error from Pohat-Adams model was selected. This model explains that the absorption rate is proportional to the residual capacity of the adsorbent and the concentration of the adsorbent. The maximum absorption capacity was found at the optimum parameters condition, which were 100 ppm of initial lead concentration at a flow rate of 10 ml per minute and at bed height of 0.06 cm. From this figure, we can summarize that the relatively lower concentration, lower flow rate, and increased bed height were desirable for higher absorption capacity and better removal efficiency. As a conclusion, the GPN membrane demonstrated good comparative properties to the commercial membrane in terms of absorption capacity and removal efficiency. The development of GPN membrane is the best alternative to revolutionize wastewater treatment and beneficial for making this technology accessible to Malaysia. Before I end this presentation, I'd love to acknowledge and say warmest thanks to IIUM and Bioenvironmental Engineering Research Group, especially to all my supervisors and contributors in this project. Thank you very much.